Modern datasets are massive. When you collect thousands of overlapping features, say in a raw medical imaging dataset, it creates a wall of visual noise. You might assume that collecting more data points makes a predictive model smarter, but in machine learning, we run into the curse of dimensionality. After a certain threshold, adding more features actually degrades the algorithm's performance. Each new dimension exponentially increases the volume of the geometric space. This causes computational bloat, severe overfitting to the training data, and structural redundancies where multiple variables tell the exact same story. To solve this, we must translate raw data into rigorous matrices, standardize the geometry, and systematically strip away those redundant dimensions. This document outlines our academic roadmap for Unit 2. We are focusing on dimensionality reduction, which requires understanding data matrices, data preprocessing, and finally, principal component analysis. In predictive modeling, a higher volume of features does not equal deeper insight. The noise of too many dimensions actively obscures the underlying mathematical truth. The foundational step in this process is translating a raw spreadsheet into a uniform mathematical matrix. In this matrix space, every individual horizontal row represents a single observation or instance in our dataset. Conversely, every vertical column represents a distinct feature or variable. By locking the data into this structure, we can use linear algebra to manipulate, scale, and transform the entire dataset simultaneously. This table breaks down the critical roles of data preprocessing. Before we can reduce dimensions, we have to normalize and standardize the inputs. Calculating the mean of a data matrix allows us to establish a baseline, impute missing values, and detect mathematical skew across the entire system. But the real danger lies in unscaled data. If you feed an algorithm raw numbers that mix a salary in the hundreds of thousands alongside a GPA measured in single decimals, the geometry breaks. Algorithms that calculate geometric distance will look at this unscaled space and falsely prioritize the variable with the massive numerical range, completely ignoring the smaller one. We apply column standardization to force all features onto a level playing field. The data is compressed and centered precisely around a zero origin, so every variable carries equal geometric weight. Without that strict standardization, geometric variance is meaningless. Any distance-based algorithm will simply output distorted, unusable results. Once the individual features are scaled, we have to analyze how they interact with one another. We measure this through covariance estimation, a mathematical assessment of how two variables change together. If we plot two variables and they increase at the exact same rate, they form a tight positive correlation. We call this multicollinearity. When independent variables are highly correlated, they are carrying redundant information. We don't need both. To find these redundancies at scale, we use a covariance matrix grid. The off-diagonal cells immediately flag the highest mathematical correlations. Identifying high covariance gives us the mathematical proof needed to know which dimensions can be safely eliminated without losing the core structure of the dataset. Once we know the redundancies exist, we have two distinct approaches to solving the dimensionality problem. This comparison table outlines the mechanical differences between feature selection and feature extraction. Feature selection, or subset selection, is the act of choosing a smaller, highly relevant subset of the original variables and discarding the rest. Mechanically, you look at a multidimensional space and physically drop one entire axis, flattening the data onto a lower plane. Because you are keeping original variables, the resulting model maintains high human interpretability, but you risk permanently erasing latent information hidden in the discarded dimensions. Feature extraction takes a different approach. It captures the essential information from the original data and represents it in a new, highly compact space. Instead of deleting an axis, a completely new, optimal axis is forged directly through the densest cloud of points, and all data is projected onto it. This approach handles nonlinear relationships well and prevents the loss of subtle data correlations, but it can introduce mathematical noise if the extracted features aren't perfectly aligned. Feature selection curates existing reality. Feature extraction mathematically forges entirely new variables, trading human readability for data density. This brings us to principal component analysis, or PCA. As defined in our text, it is the most widely used statistical procedure for feature extraction. PCA utilizes an orthogonal transformation to convert a set of highly correlated variables into a completely uncorrelated set of principal components. Its prime directive is to map data into a lower dimensional space, while ensuring the variance of the data in that new space is strictly maximized. The geometric logic here is straightforward. The higher the variation spread across a feature, the more information that feature carries. To find the first principal component, the algorithm dynamically rotates a line through the correlated data until it locks onto the exact angle that maximizes the spread of the points. This is PC1. Then it draws a second line, strictly orthogonal to PC1. This is PC2, positioned to capture the maximum remaining variance. This list highlights the specific advantages of this method. By maximizing variance along fewer axes, PCA achieves rigorous dimensionality reduction, eliminates multicollinearity, and enables highly efficient data compression. But there are strict limitations. As noted in the text, PCA is extremely sensitive to data scaling, and the resulting principal components can be difficult to interpret. Because these components are linear combinations of original variables, the labels disappear. The resulting model becomes a black box, making it exceedingly difficult to explain the results in real-world terms. PCA is a highly effective yet destructive process. It aggressively optimizes the geometry of the dataset, but it trades human interpretability for maximum algorithmic efficiency. We start with chaotic, raw features. We translate them into matrices, neutralize their scales to a zero-mean grid, and mathematically compress the variance down to its tightest possible plane. Trimming these dimensions guarantees that our downstream algorithms won't suffocate under the weight of mathematical noise. With the redundancies stripped and the geometry standardized, the data is now structurally primed for predictive modeling through classification and regression. Dimensionality reduction is the rigorous mathematical distillation of data down to its